Welcome back.
So far we covered lesson one overview, lesson two, and then today we are covering CT.
I listed some reference that you can use to uh, enhance your knowledge, but the slide that I have today should be sufficient. But if you're interested in to learn more, you may as well uh, look for these references. Especially there's a video that I found in YouTube by Dr. Cleozzi. This was very useful for me. So if you're bored, you can use those. So CT imaging in radiation therapy. CT is very, very important in radiation therapy. So it basically replaced conventional simulators. That's why we still call it CT as a CT simulator. I'm not sure you guys are familiar with conventional simulator. So conventional simulator looks just like our linear accelerator, but instead of having MB, therapeutic beam on the gantry, we have kilovoltage imaging. So just look like a LINAC, but instead of a megavoltage source, it has CT. It's like rather kilovoltage X-ray. Then instead of MB imaging panel, we have kilovoltage imaging panel. So you would place a patient just like we do the Simon set, and then you can set your gantry angle, you can set your collimator angle and size, and so forth. That's how we used to do it in 2D simulation. But with the introduction of CT simulator, now we can acquire three-dimensional imaging of the patient, and then we can, if we want, we can even generate digitally reconstructed 2D images, which I'm going to talk about a little more later. Okay, so the key concept of CT is it provides three-dimensional anatomy, okay, for both target volume, then critical organs. Okay. So one big advantage of using CT is its geometrical accuracy is very superb, okay, as compared to MRI. MRI has some inherent geometrical distortion that physicist has to correct for. Okay, but CT provides very, very accurate geometrical representation in 3D. And the other key advantage of using CT is it provides density information for heterogeneity corrected treatment planning. So in old days, we acquired patient contour and then we treated all the body as a water. Okay, so it was rather crude, those calculation. Then it didn't work very well for heterogeneous medium such as lung or sinus or bones. But because CT provides this density information, treatment planning system can account for different attenuation through the body. Individual CT image itself is 2D, like slice by slice. But as we contour slice by slice, then we can build a three-dimensional model of anatomy. Okay, either be OAR or target. So on your left, it is basically stacked outlines of contours, and on your right, it's actually three-dimensional representation of the anatomy. Let's talk about beam's eye view that is generated from the three-dimensional CT. Okay, so if you have three-dimensional information of patient, okay, you can create this beam's eye view two-dimensional image. Okay, so say we call this as digitally reconstructed radiograph. This is actually reconstructed 2D radiograph. Okay, so what we acquired in CT is 3D, but here you see here is 2D. Okay, so how did it? How was it created? By following through each ray by ray along the patient 3D. Then as it as each ray goes through different anatomy, you have this variation of attenuation that creates this, grayscale. Okay, so as you turn the gantry, then here you create lateral DRR, again, digitally reconstructed radiograph. Okay, so in short, there's a synthetic radiograph produced by ray tracing from a virtual X-ray source. Okay, so traditionally, we created this 2D image using conventional simulator. Okay, so the patient would stay, lie on the bed, and then the gantry with the KV source would rotate around the patient, then shoot the KV, and then acquire real 2D port image. Whereas with the CT sim, we create this digitally reconstructed image inside treatment planning system. So how are the CT images are created? Okay, in short, the CT images the internal structure, internal structure of an object by reconstructing cross-sectional view from multiple projection of the object, and produced by attenuated T-beams. So I'll go in detail, but basically the key here is multiple projections, So it's not just single projection like chest X-ray. It is multiple projection from all different around angle. So at different projections, and another projection, and then another projection, and so forth. So each projection has some attenuated X-ray image profiles, and then the computer will reconstruct the image. All right, this gentleman here is Dr. Hounsfield. The Hounsfield name comes from his name. He's a British engineer. He invented first CT scanner, and he later received Nobel Prize in medicine. So this is actually his picture with the first CT scanner. Then it was actually just very small, Then the image quality was, compared to modern CT scanner, it was actually only very, very poor resolution, and also took a very long time to acquire image. But you see this image is the first image of human using CT scanner. You see the brain tumor there. So before we go into the depth of CT image reconstruction, let's talk about attenuation. What is attenuation? So if you have an X-ray source to your left and radiation detector to your right, and then if there's no object in the middle, assuming it's a vacuum, your initial intensity will be captured. This I naught is intensity. There's no change in the intensity. But if you have an object with the thickness of D, and then say the material property says mu, mu is constant, then the amount of radiation that is detected by the detector will be depending on the total thickness and then material composition. So in simple uniform attenuation, it is exponentially decayed. So the intensity at the detector is original intensity I naught times exponential decay. It is actually a combination of this mu constant and the thickness of the object. So the thicker the object is, the less of intensity you will receive. And the material composition, the density, you can say density or linear attenuation coefficient. Say if it's lung versus bone, it changes how much of a radiation will detect after X-ray pass through. For example, if you have a 1 MeV X-ray, mono energy X-ray, the linear attenuation coefficient of the liquid water is 0.07. The linear attenuation coefficient unit is inverse length. So let's calculate after 10 cm of water, what is the transmission? Okay, so the way you calculate this is the ratio between, as I showed this, right? So basically intensity after 10 cm of water over the original intensity is this exponential, okay? Negative expansion because exponential decay, and then is a linear attenuation of the water, which is 0.07, and the thickness of water. So basically how much of water it goes through. So that is about 50%. So in other words, if you have 1 MeV X-ray, then if that 1 MeV X-ray goes through water of 10 cm, you lose about 50%. But human body is not water, right? So our human body has heterogeneity. In this example, we have a liver, we have some rib cage, then we have a vertebral body, then some fat and tissue. So if X-ray, say in this case, like think about this as a pencil beam, as it goes through these different materials, so how do you account for the attenuation? So you can use this simple equation where you sum all these individual pixel property with the pixel size. Okay, so mu I is the attenuation coefficient along some segment I, the length of x I. Okay, so if you have 10 different materials with a fixed size of, I don't know, like 0.5 cm, you can calculate the total attenuation by using this equation.
I'll attempt to explain this CT reconstruction algorithm with this 2D object. Okay, so conceptually, imagine you have this two black box inside this white bigger box, and by using this projection and reconstruction, we can find out what's inside. Okay, so by project one direction from one direction, so say if we have X-ray source is up top, then say imagine you have some parallel X-ray coming down from the top, and because we have object here and then there, your detection panel will detect something along this path, right? So then it will report, okay, along this path I detected this much of attenuation, right? Since we have only one projection here, this projection or this detection cannot differentiate where that object is. However, it can at least tell that there is object. Okay, now let's throw in another projection. So by projection, this time we have X-ray source coming from your right. Okay, and then because we have object here and here, again on this detector panel, you will detect attenuation through one-dimensional attenuation. So your detector say, okay, I detected something here, I detected something here. Okay, so far we can at least tell, okay, there it looks like there's an object. So it looks like there's 4 objects with this two projection. In reality, there's only 2. Okay, but now let's throw in another projection. So this time the projection is coming from this angle. Okay, and then the detector at the opposite side will detect, okay, I detected something along this path. Okay, and I detected something along this path. So now you can tell that, okay, as we add more projection, the chances of detecting the actual object is getting higher and higher. So I want to introduce the concept of filtered back projection. Okay, so before it was just simple back projection, which has some blurring, okay, inherent blurring. So in this view 1, 2, 3, when you have an object, you end up detecting something like this, right? So the signal is something like this, and from these 3 projection, if you reconstruct, you end up having the object with some blurred image. Okay, But if you filter each projection using special imaging filter, instead of having this shape of detection, you can have something like this, where you have dip, at the boundary. Okay, so if you reconstruct using this filtered images, you end up having some clear object reconstructed. Okay, so that's the concept of filtered back projection. Okay, so in this view, I'm showing an example of when you have a projection of 180, okay, instead of just 103 or things, you develop this very nice reconstructed image of internal. Okay, so this is filtered back projection, and this is raw back projection reconstruction. So it's important that we use filtered back projection. So, well, as you increase more projection, the image quality will be better. So CT image reconstruction technology has evolved significantly ever since the introduction of the first generation. So first generation CT can be categorized as rotate and translate, okay, using pencil beam. Okay, so this image will show is showing first generation CT tomography. So you have an object, then this is detector, and this is X-ray source. So it is a pencil beam. Okay, so that means from your left to right, you reconstruct this one line at a time. Okay, so you translate by moving the X-ray and source pair. And then once you finish this line, you rotate your source and detection pair, and then continue. Okay, and then rotate and translate, rotate and translate. Okay, so that was our first generation. And second generation is very similar, but instead of using pencil beam, it uses narrow fan beam. Okay, so it grabs more anatomy. So third generation CT can be categorized as rotate with wide fan beam. So in this third generation, the X-ray tube and detector arrays are mechanically attached. So and it is fan beam, wide fan beam. So with one irradiation, it can capture the whole body anatomy that's wide enough. Okay, and as it rotates, the detector panel and the X-ray source are paired together and then rotate. Okay, so with a single rotation, you can capture all those anatomy inside. Okay, however, third generation CT, you cannot rotate continuously. Okay, because otherwise the cable will be tangled up. So what it did was you rotate one direction clockwise, and then you counterclockwise rotation for the next slice. In this fourth generation CT scanner, it's called rotate and stationary with a wide fan beam. It's very similar. The only difference is instead of having detector array, it is actually a ring of detector arrays. Okay, so this is stationary. Your detector is stationary, and the only thing that rotates is the radiation source. Okay, so it's mechanically more stable maybe, but again at this point it was actually limited to the one full rotation, and then it has come back for the next rotation. Okay, so this fifth generation is more like specialized CT scanner. So it's stationary and stationary. So there's no moving part. Okay, this is not a regular CT scanner. It's a very special scanner. So it's a sort of like electron scanning. So instead of rotating the X-ray source, what you have here is the electron gun. Okay, so this electron gun is magnetically steered. Okay, and then you have these target rings. Okay, and then this electron will hit this target depending on where you are hitting. And then once you hit this target with the electron, this will create Bremsstrahlung photon, and that Bremsstrahlung photon will be detected at the stationary detector rings. Okay, so the big advantage of this 5th generation CT scanner is it can be super fast. Okay, so there's nothing rotating around, so you only steer these electron beams at a certain location, and then you capture snapshot of your anatomy. Okay, this is example here. So in typical CT scanner, the heart image can be blurred because heart is pumping while you're acquiring CT. But it's this 5th generation, also known as electron beam CT scan or ultra fast CT scan. The acquisition time is less than a second. Okay, so it is typically used for the cardiac image application, and the field of view is also very small. Okay, finally, the 6th generation. Okay, this is our current modern CT. So it is helical CT. So before, the X-ray source cannot rotate continuously, right? But this slip ring technology allows gantry to rotate continually, untethered by wire. Okay, so it is actually slip ring technologies. You have a brush contact on the ring, so the metal brush is actually skimming through, and then while it is skimming through, the electricity can still flow, so it allows the gantry can rotate continuously. Okay, so it allowed much faster rotation of the X-ray source. And what's helical about it? So the helical is if you allow table to proceed while you have stationary rotation of CT, you create this helical path of X-ray. Okay, so that helical path allowed basically it allows this gap. Okay, so you don't have to scan full width. Okay, so you allow this gap. Okay, and then you can scan or reconstruct the anatomy between this ribbon by utilizing all this information that is available from different angles. Okay, all right, in this example I'm showing you the slip ring technology. Okay, so the ring is this. Okay, you see the ring, then you have this metal brush. Okay, so as the gantry rotate, it continuously maintains the contact. Okay, and then so CT scanner is basically brushing through this ring, which is brilliant idea, and that it allowed continuous rotation of the gantry. All right, so I have a short video. I'm not sure how well it can be recorded in this video, but you can search helical CT on Google and YouTube. Okay, so let's see. Let me play this short video. Okay, so this is actually continuous rotation of the gantry, as you can see. Then it can be really fast. So the faster the gantry rotate, the less of a motion artifact it will create, right? So a lot of things are moving inside the patient body, like breathing motion, abdominal motions, but with this fast rotation of the gantry, you can overcome certain motion artifacts. In this 6th generation helical CT scanner, there is this parameter we have to define as a pitch. Pitch is defined as table advancement per 1 full rotation of the gantry divided by the slice width. Okay, so pitch influences radiation dose to the patient, okay, the image quality and total scan time. When pitch is 1, that means it is equivalent to the continuous acquisition of the actual CT. But if pitch is bigger than 1, that means it can acquire faster scan, and also it can be a less patient motion, but there is chance that image can be blurry. Okay, and when pitch is less than 1, that means we are intentionally over scanning it. Okay, so it such as 4D CT. Think about 4D CT. You guys seen 4D? Have you guys seen 4D CT acquisition? Maybe next time you are shadowing CT sim, pay attention. What is the pitch setting for 4D CT? It is significantly less than 1. That means we are over scanning. Why do we over scanning on 4D CT? Because we want to capture our 10 phases of breathing, right? So it will overscan by moving the couch very, very slowly. Okay, but you end up having increased patient radiation dose, of course. Okay, so just think about the helical path, the image that I showed you earlier slide, and pitch. That example has a pitch bigger than 1. Okay, and pitch smaller than 1 means overscanning. The ribbons around the patient has some overlap. Okay. Okay, so here's another example, or another explanation here. So when I say pitch is 1, there's no gap between this fan beam covering the whole body. Okay, so as it rotates around the patient, there's no gap. Okay, X-ray fan beam will cover entire body. Okay, however, when pitch is bigger than 1, that means some view angles. Okay, view angles meaning that when X-ray rotates around the patient, some angles will not be covered by the beam width. Okay, at certain table rotation. I'll explain this next slide, but which is the beauty of this helical scan. You don't have to have pitch of 1 to reconstruct certain cut. Okay, but when pitch is less than 1, that means the beam width is actually, there's significant overlap of beam width, okay, at each angle. So like I said, in 4D CT, we deliberately slow down the table advancement speed, okay, so that we can capture the full 10 phase of breathing. Okay, so in this example, pitch is obviously bigger than 1, and when you reconstruct a slice at this Z location, it interpolates data that is before and after to recreate this actual cut. Okay, so the acquisition is kind of helical with this little bit of angle because we acquired the image while the table is moving, but you have to reconstruct this actual cut by using this neighboring information. So what kind of detector is there for CT scanner? Okay, so earlier version had this xenon detectors. So it's high pressurized xenon gas chambers, that it has chamber arrays rather. Okay, it's long thin cells, okay, between two metal plates, and the detector has this angle focused to the X-ray source, and then when X-ray comes in, it ionizes xenon gas, and then it can detect the signal. Okay. So here's a different types. It's a more modern type of detector, which is solid state detectors. So it's a scintillator. You see here, it's coupled with photodiode. Okay, so X-ray comes in, then it creates this scintillation, and the scintillation light is captured by this photo tube. Okay, so conceptually very similar to the DR system that we learned previous lecture. Okay, so you might have heard about this multi-detector CT scanner. So what do we have in our department? Is it multi-detector? Yeah, it is a multi-detector array. So our department has 16 slides. So what does that mean? Okay, 16 slides. And if you go to radiology department, they have 256 multi-detector arrays. So what it means is, so say on your left, okay, this is single slice, one long detector. Okay, so that means this is actually patient head. We're scanning brain here. Then X-ray source has a fan beam with a certain width. Then this detector here is a single detector. So that means you acquire one slice at a time. Okay. But on your right, you have a multi-slice detector. So that means with this same one fan beam, you can acquire, well, this is exaggeration. I don't know how many, actually, maybe this is 16. So you can acquire multiple signals along this slice. Okay, so with a single shot, the same collimated X-ray fan beam, you acquire one, but you acquire multiple signals. Here's another view. So with the single detector array, you acquire one single slice at a time. With the one rotation of X-ray, you get one slice. However, in multiple detector array, in this example, we have what, 1, 2, 3, 4, 5, 6, 7, 8 detector arrays. Your slice thickness can be configured, okay, in different ways. You can get as many as 1, 2, 3, 4, 5, 6, 7, 8, or you can bin these two arrays to acquire one slice. So in this example, we acquired 4 slices, even though our detector can have 8 at a time. Okay, so you might have noticed that at the CT sim we can acquire various slice thickness. It's not just 1 millimeter; it can be 1.25, 1, 2. So that's because we have 16 slice detectors. Right. So let's talk about the relationship between the image thickness and image noise. Okay. So what is noise? Let's define noise is the function of well, all the noise. Noise is actually the image is grainy. Then if noise is high, that means your CT scanner is noisy and grainy. Okay, so it is inversely proportional to the square root of number of photons. So that means the more photons your detector receives, the noise will be reduced. Okay, so number of photons increase, your noise will go down. Okay, so in this example, I have slice thickness of 5 millimeter across. Okay, and let's define this relative noise. This is our actually norm. Okay, so you have 100% relative noise, then required current. Okay, so you can, in other words, say a current can be a number of photons. Say let's define as 100. Okay, and then let's compare to other situation. If your slice thickness is reduced by half, okay, so 2.5 millimeter, and if you use the same current, okay, you end up having the noise of 141%, okay, because the number of photons that is coming to the detector is cut by half, okay. And then if you want to achieve same amount of noise, okay, relative noise, you have to increase your current, okay, by the factor of 2. Okay, and if you want to reduce your slice thickness even further down, 2.25 millimeter, that is 1/4 of our standard, the same situation, your noise will be twice as high. If you want to achieve the same relative amount of noise, you have to increase your current, tube current, by 400%, okay, and so forth. So another means better Z resolution. Typically, when we say better, that means thinner. Okay, so SRS situation, we use 1 millimeter, and then if we have a spine SBRT, we want really thinner slice. And if you have like HDR, when you have a different shapes of applicator or catheters, we need this 1 millimeter and sometimes sub-millimeter slice thickness. Okay, so that means if you don't do anything, you end up having increased noise. Okay, Then if you want to reduce the noise, you end up increasing tube current. That means your patient imaging dose will inadvertently, unavoidably actually increase as well. So in CT, there's this thing as Hounsfield unit, okay, or CT number. So the CT number is defined like this. Okay, some constant, typically 1,000 Hounsfield unit, 1,000, and it is relative to the linear attenuation coefficient that of water. Okay, so if you have a one material like a bone or lung, the CT number of that material is defined as 1,000 times this relative linear attenuation coefficient. Okay, so here's some examples of CT numbers. Okay, the air is typically, well, not typically, if there's nothing vacuum, you will by default have negative 1,000 because that is basically 0, and then negative mu of water over mu of water, this will be negative 1, and then you end up having CT number of air will be 1,000. Okay, and it can be as high as 3,000 for the dense bone, cortical bones. And what about for the water? Okay, for the water, if you scan water, by definition, the CT number of that it will be 0, right? So the lung is very close to air. Then you have a muscle. Then you have soft tissue that is denser than water, right? And then if you have fat, that is actually less dense than water, so it will look a little darker than the water or muscle. So in CT scan, this is wider, okay, say brighter, and then this is darker, okay. All right, but just remember, okay, CT scan of the water, by definition, if it is well calibrated CT scanner, the Hounsfield unit of that material, water, should be 0. So in radiation therapy, we have to relate this CT number to the electron density, right? So how do physicists develop this correlation? By using this, what we call density phantom. Okay, this phantom, you might have seen it before, has each plug has a different density, okay, electron density relative to water. It even has actually tube that you can fill it with water. Okay, so if you scan this with a CT scanner, you will have a Hounsfield unit of each scanner, and then you also have the physical composition of that plug. Okay, so physicists can develop the correlation between CT number and then electron density or physical density of the plug. Okay, so this phantom can be used to commission your treatment planning system. Also, this phantom can be used for monthly constancy check. All right, so I want to conclude today's CT lecture by introducing what kind of different artifacts can a CT scanner have. Okay, so there are many different situations, but I will introduce 4 different situations: ring artifact, and partial volume artifact, and photon starvation artifact, and then metal artifact. Okay. All right, so first, ring artifact. Okay, what is ring artifact? When you have a detector array going bad, okay, say you have a one bad detector here. Because CT scanner is a rotational acquisition, and then CT X-ray source and the detector array is paired. So if you have bad detector, it'll be bad, along the full rotation. So when one or more detector arrays are miscalibrated or malfunction in 3rd generation CT, even in 6th generation CT, you end up having this ring artifact. Okay, so then physicists has to recalibrate or fix that. Okay, so this can happen on CT, cone beam CT at the unit 2. You can end up having this ring artifact. That means we need to replace the detector or we need to recalibrate. Volume averaging effect can be defined as this blurred image that does not exist at this yellow slice. Okay? So strictly speaking, if you create CT image at this CT location, there's no part of pancreas, right? But when we acquire CT with this discrete volume. And because of this volume averaging, your cut at this yellow position can have this blurred part of the pancreas. Okay, so the remedy for that will be you have to use thinner slice. Okay, but we just talked about it. Thinner slice requires a higher tube current. Here's another situation of partial volume effect. So if you have off-centered, very high-density object, okay, such as pacemaker, okay, the object protruding part way into the width of the X-ray beam. So when we acquire image and gantry angle of this, we'll not see this object. Whereas if you rotate to the other side, this acquisition, this beam, will see this. So you end up having this blurred object. Okay, this is not a representative the acquisition of this, but it's an example. Okay, so you have ended up having some blurred edge of the high density image. Okay, so like I said, what is the solution for this blurred partial volume artifact? You have to choose thinner slice thickness, okay, whenever you expect some abrupt anatomy change. Next example is photon starvation artifact. When patient thickness is changing a lot with regard to the gantry angle. So typically at the shoulder level, patients are thinner in this way and thicker this direction, right? So if you set certain tube current, say you have X-ray source here, you need actually higher tube current when we acquire this. Whereas when you acquire your CT scan with the gantry up here, you don't need as much tube current. So this discrepancy of the required CT tube current to achieve same image noise is different because a patient is not cylinder. Okay, so you end up having this black streak of an artifact, and we call them photon starvation artifact. Okay, so what is the solution for that scenario? Okay, so modern CT scanner has this tube current modulation. Okay, so it is adaptively changing tube current based on the response of the detector at the opposite side. So unfortunately, our CT sim does not have this feature, but I believe most of the radiology CT scanner has this tube current modulation technology. Okay, it adaptively dynamically changes tube current, and then so overall, you can achieve same or better image quality with reduced tube current. What does that mean? That is actually, more optimized patient imaging dose. All right, so metal artifact. Most of you guys actually are already familiar with this. So why do we have metal artifact or high density artifacts? So in this example, the patient has some dental filling with some high density material, and then you have these two things, right? One is this black artifact here. I'm sorry. And then you have this bleeding of this white high density. So it is twofold. Okay. So why it is happening? It's because the X-ray beam is significantly attenuated. Okay. So not enough number of photons can reach the detector. Okay. So they're basically corrupting projection data. Okay. So it can be dental filling in this example, or prosthetic devices like hip replacement, or some surgical clips. Okay. So what do we do in our department? We in this example, our dosimetrists would contour this as an artifact and then assign soft tissue density in treatment planning system. Or we can use OMAR scan. Okay, you've seen this OMAR scan in our CT scanner. So it's a software approach, the algorithm. So it's orthopedic magnetic artifact reduction technique. Not magnetic, sorry, orthopedic metal artifact reduction technique that can take care of this metal streak artifact by the software approach. The algorithm actually takes care of that and making artificial image that is more close to the real anatomy. So what are some considerations when it comes to the radiation oncology CT scanner as compared to the radiology CT scanner? Okay, so our CT scanner has flat top table, not like comfortable curved top, the radiology have. Okay, why? Because our treatment table is also flat. Okay, so when you acquire image, ideally when you take PET CT of your radiation oncology patient, you can actually add this removable flat top couch and then acquire PET CT in flat top table. I mean, you might have noticed that like when our CT scanner is down, sometimes we scan our patient in radiology department. So the first thing that we want to make sure is we attach this removable flat couch top onto that radiology department couch top so that we can acquire patient with flat top. Our CT scanner has a larger bore size. Okay, so radiology department CT scanner has a smaller bore size, but ours has to be big. Why? Because we have to accommodate this unusual patient position. Sometimes our patient has to raise their arm, sometimes they have to bend their knees fit for scanning. And then we have these immobilization devices. We have a breast board, thorax board, belly board, all sorts of different devices, right? Prone breast board type of things. Okay, so also the other aspect is it is important for us to include full width of patient extension. Okay, why? Because we need to calculate the treatment planning. Okay, the dose. So if you have a patient with arms, okay, so we have arm and patient torso and arm. If patient cannot raise their arm, but we have to treat lung, for example, we have to acquire this patient's arm, to know where it is. Whereas in a lot of times in diagnostic CT scan, they can reduce the field of view to this. They don't care where arm is because they only care about where the tumor is or where the disease is. So our scanner is typically bigger than 70 cm bore size to do this. What is the downside? Okay, the downside is if your detector, the CT scanner bore is big, your X-ray source and the detector distance end up being, it has to be, larger, right? So you have inherently the image quality is not as good. Image quality can be bad. Okay. So patient orientation. So parent, especially this is not an issue actually nowadays. But in old days, it was very important that we made sure that head first scan. When we scan head first scan, we have to indicate that. Then that information has to be correctly carried over to the treatment planning system. Okay, so this is especially important when we acquire CT image or MRI image from another department or another institution, because there's a chance that the way they commission their machine can be slightly different. Okay, so when you acquire head first scan from upstairs, the treatment planning system has to recognize that as head first scan. Okay. All right. So I think that's all I have. And we covered a lot today, so please take time. You can review this video, replay this video. Then if you have any question, feel free to email me, okay, or contact Charlie for more question. Okay, thank you.